Let's take a look at density. We know that density is a physical property. It's a physical property of matter. And density can be calculated by looking at the mass and the volume of a substance. So, density is mass per unit of volume. And one of the labs that we did in class is making a density column. So, we measured out a specific amount of volume of each liquid, and then we poured those liquids into a graduated cylinder. Those liquids generally did not mix together. Because of the density of those liquids, they formed layers on top of one another, similar to this density column that you see here. This column not only has liquids, but it also has solids that are included with it. And we know that the substances that are the highest in density, the ones that have the greatest density, are going to be at the bottom. So the bolt and honey and corn syrup, those are things that are going to have a great amount of density. The substances that have the least amount of density are going to be at the top: the lamp oil, the ping pong ball, rubbing alcohol. So those things have less density than the substances that are below them. So what variables do we need in order to calculate density? We need two things. We need mass and we need volume. So when we look at density, we can take those two variables and do a little bit of magical math, and then we can figure out the density of a substance. So all we need is mass and volume in order to calculate density. So what is mass? Mass is the amount of stuff that is in a substance. It's the amount of matter in a substance. And mass is going to be using the base unit of grams. Sometimes it's larger objects, it will be using kilograms. And mass is usually going to be measured by a triple beam balance, like you see in this picture here. It's called a triple beam balance because it has these three beams. And you move these masses, and that will help you to calculate the substance or the solid that you place on the pan over here. And we also have these digital balances, and these are the ones that we're primarily going to be using in class. What is volume? So volume is going to be the amount of space that an object takes up. And in order to measure volume, we're going to use something like a beaker or a graduated cylinder, and that will help us to determine the volume of a liquid. So the numbers that you see, these graduated numbers on the sides of these beakers, those are referring to the volume of a liquid. So when you look at the volume of a solid, or when you're calculating the volume of a solid, you can use different equations. And these are ones that you probably have talked about in class. So we are generally going to be looking at this one here and looking at the volume of an object that is a cube. So that will be length times width times height. And that will help us to determine the volume of a solid. And when we're looking at a solid, the units are usually going to be centimeters cubed. And the fun thing about cubic centimeters is that cubic centimeters equals milliliters. So we can use those units interchangeably if we need to. So how do you read a graduated cylinder? Well, you look at a graduated cylinder, you figure out what the graduated lines are on the side and what they're counting by. For example, this one, we see a 10, we see a 20. There's 5 going to be marked somewhere in the center here. And this looks like, at first glance, it is counting by 1. So let's see, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we figure out what the graduated cylinder or the beaker is counting by, and that's going to be the first step in getting started. So when we're looking at a graduated cylinder, one thing that you'll notice is because of the surface tension on the molecules in whatever liquid it is that is in the graduated cylinder, that a lot of times we're going to see kind of a curved surface, and that's going to be the meniscus. And that's because the molecules are pulling on one another, but they're also sticking to the sides, they're adhering to the sides of the graduated cylinder. And so it's all kind of pulling tight across that surface. So that surface tension is going to cause a little bit of a dip in the surface of the liquid. So that is called the meniscus. And when we read the level of the liquid, trying to determine the volume, you need to make sure that you're looking straight on at eye level and also reading from the bottom of the meniscus. So right here, it looks like that the volume of the water is going to be 15. However, if you look at the meniscus, the water's dipped downward here. So the water level is actually going to be 14. So that's a little bit tricky. Make sure that you are looking straight on at the top surface of the liquid in order to determine the volume. Another method of determining volume is displacement. So displacement is when you have a liquid like water, and then you put another object into that water, and the water level changes, the water level increases. For example, if you run a bathtub full of water all the way up to the tippy top of the bathtub, if you sit down into the bathtub, that water's going to overflow. Well, why does that water overflow? Because you've added additional mass into that tub. You've increased the volume that is in the bathtub. So we use that principle in order to help us determine the volume of an object that has an irregular shape. So if you know the starting volume of a liquid, and usually this is going to be using water. So if we know that the starting volume here is 50 milliliters, and then we place a rock in here. So the rock has been placed into the graduated cylinder, and now the water level has risen. So it has displaced a specific amount of liquid. So that amount of liquid that has been displaced is going to be the volume of the rock. So if we read this and our starting volume is 50, we've added the rock now and our ending volume is 75, then all we have to do is subtract. 75 minus 50 gives us 25 milliliters. So that tells us that the 25 milliliters that was displaced is the volume of the rock. And this is tying in Archimedes' principle. So how do you calculate density? We were just talking about how density equals mass over volume. So this fun little triangle here helps a lot of people to kind of keep these straight. So we've got mass at the top, we have density, and then we have volume. So that is one way that a lot of people keep track of our equations for determining density, mass, or volume. So since there's those three variables, if you know any two of them, then you can solve for the other one. So for example, we know density equals mass over volume. We also know that mass, which is the top of our triangle here, equals density times volume. And volume, which is our other variable, volume, equals mass divided by density. So this triangle helps a lot of people in order to determine what our equations are for solving for mass and volume. The density of water is really unique. So water is a unique substance because a lot of times when different materials will change state or when they change phases, a lot of those substances are going to increase in density from liquid to solid. So this is really important to water because when water becomes a solid, it decreases in density. So it kind of acts opposite to a lot of different materials. So that's really important to ecosystems because if you think about a lake, for example, that has aquatic animals, it's got fish swimming around in it. If the water were to freeze on top of the lake, if the temperature's dropped and the water's freezing, then the water that freezes is just going to be the surface of that lake. However, if the opposite were true, if water acted like most other substances, then the density of frozen water would be much higher than liquid water. And that would mean that basically the lake would freeze from the bottom up, and that would kill all the organisms that were living in that lake. So it's really important to us as a biosphere and ecosystem that water acts conversely to a lot of other substances. And in water, when water freezes, when it goes from a liquid to a solid, it becomes less dense, which is also another property that allows ice cubes to float in water. So in looking at the density of water, the numerical value for the density of water is going to be 1 gram per centimeter cubed. And this is going to be a number that we're going to refer to a lot. So you can see that in looking at the density going from the density of liquid to solid, the density is going to shift and it goes a little bit lower. And so that's why the ice is able to float in water. So this is looking at the molecular structure of different phases of matter, and just to kind of give you an overview of how molecules that are varying densities will act. So if you look at A, we have a bunch of molecules that are packed into the same amount of space as these other squares. B, they're kind of spread out. C, they're spread out a little bit. D, spread out a little bit more. So when you're looking at these, the one that has all the particles close together, that's going to be the highest density. So letter A here has the highest density because it has the most matter packed into a specific amount of volume. Whereas if you look at B, it's got the same amount of volume. It's taking up the same amount of space. However, it doesn't have nearly as many molecules. They're able to spread out. They have spread out a lot. So this is kind of an example of a gas. So this would be the greatest amount of density. This would be the least amount of density. This would be the second to least, and this would be the second to greatest. So just to put those in order for you, the lowest density is going to be the one that has just a couple molecules in it. The greatest density is going to have the largest amount of molecules. So there are a couple different variables that impact density and can shift and change the density of a substance. So if you have an increase in temperature, then that's going to cause a decrease in density usually. So if we're looking at water, for example, so this is room temperature water. So this is what room temperature, 68, 70 degrees, this is what the water molecules would be acting like. They would be spread apart a little bit. So if the water were cooled down, then those molecules would be moving a little bit closer together. So this is not talking about when it's frozen. This is talking about chilled water when it's in the refrigerator, for example. If you were to heat the water up, then as you're increasing in temperature, it's going to be causing the density to decrease. Those molecules are going to be spreading apart. And this is going to be an example of how liquid water will be changing, heating up and changing into a gas, into water vapor. Another example of that will be hot air balloons. So in order to get the hot air balloon to lift off the ground, has to be heated up. Looks like it's being heated up a lot. And that's going to cause the molecules to spread apart. So that's decreasing the density so that the hot air balloon is able to get aloft. This is looking at one of our labs, our ice melting lab. So salinity is another variable that can impact density. And if you increase the salinity, the amount of salt in a substance, then that's going to increase the density. And we were able to see this in our ice melting lab because the salt water, the water that had salinity, was going to stay at the bottom, where the ice cube stayed at the top, the fresh water stayed at the top, and even when it began melting, it was at the top. Whereas the fresh water, which had similar density to the ice cube, as the ice cube was beginning to melt, it all just kind of started mixing together. So an example of that is looking at our polar ice caps and global warming. So if we go back to this slide, we know that an increase in density is going, or an increase in salinity is going to cause an increase in density. So what do you think would happen if the reverse case? So what do you think would happen if we have a decrease in salinity from additional fresh water? So what do you think, what would you predict might happen in the future if there is diluting of the salt water from the addition of all that fresh water from melting polar ice caps? So think about it and see if you can figure out what might happen to our ecosystems. And our last example of how density can change is with pressure. So if you have an increase in pressure, then that means there's going to be an increase in density. So an example of that is looking at atmosphere or looking at the ocean. Both of those show us examples. So this would be an example of on Earth's surface, we're going to have a lot of mass, a lot of matter, air molecules that are pressing downward on substances that are right near Earth's surface in the troposphere. Whereas further up in the atmosphere, the molecules are going to be more spread apart. There's going to be less density. There's less weight and mass of the substances of these air molecules, so there's not as much pressure. So if you think about a balloon as another example too, if you blow up a balloon, you are adding more air molecules, you're adding more matter, and those molecules are going to be bouncing around because they are a gas. And so what happens if you add pressure? If you're increasing pressure on the outside of a balloon, what's going to happen to that balloon eventually? It's going to pop. So why would that balloon pop? Because you are adding pressure, and that addition of pressure is going to be causing an increase in density. It's making all those molecules smush down into a smaller volume of space. So another fun example, this is from when I've been out to sea on a couple of occasions on ocean research trips. So this is not the shrunken head that I did. Mine is at home, but this is just an image to show you this. So this is a styrofoam head. And what I did is I found a styrofoam head at like a craft store, and then I decorated it and sent it down to the very bottom of the ocean on the ROV, on the remotely operated vehicle, which is like an underwater robot. And so as the styrofoam head descends, it gets smaller and smaller. So that addition of pressure is affecting the density. It's causing it to smush, and you can see eventually it ends up pretty small. But one thing that I noticed is in actually holding the styrofoam head that I'd sit down to the bottom of the ocean, it felt heavier. It wasn't heavier. It just felt like it because all those particles had condensed, they had all smushed together. And so that pressure had increased the density. And this is another example. And this actually is a picture of one of my cups. So I had a cup that was full size, styrofoam cup, just regular styrofoam cup. And I decorated it, of course, because why not? And sent it down to the bottom of the ocean. And again, it smushed because of the pressure.